the calculation of the interpolating polynomials by using this idea of systems of equations is a bit too complicated. So the Newton basis greatly simplifies the actual approach, and the way it's able to do this is by producing a different notation for the polynomials. We essentially record them in a different fashion. Here is how the polynomial looks. So let's consider for example, a polynomial of the third degree. So we're going to have cubic splines being used to model some function. So polynomial of a third degree with the Newton basis approach is described as follows. It's going to be a set of coefficients. I'll actually no longer call them a, b, and c, and so on. I'll just call them a0, a1, a2, and so on. And a0 is actually going to be the lowest order. So a0 is going to be the constant, a1 is what's going to be in front of the x, a2 is what's going to be in front of x squared, and so on, just to alleviate the confusion. So with the Newton basis, we rewrite the polynomial as follows. We say that it is a0 plus a1 times x minus x0 plus a2 times x minus x0, x minus x1, plus a3 times x minus x0, x minus x1, x minus x2, like so. So this is our new way of writing the polynomial. You'll see that it involves a lot more because essentially now it's directly incorporating not just the constants of multiplication but also some values of the actual function. So how can we use this, and why does it matter? Why does it matter that we have this kind of notation? And the reason is that essentially if you think about this in terms of a matrix, then instead of solving a system of equations, essentially instead of an n by n matrix, it's still an n by n matrix, but it's triangular. So finding the values of a, giving the values of x and f of x is actually really easy. So let's draw a table of some values and we'll try solving this. So let's have a very simple table with a set of x and f of x values. So I'll have some, let's have 4 values because that's what matches the description up above, even though we can extend it to any kind of polynomial. So we'll have the values 0, 1, 3, and 4. You'll notice they don't really have to be contiguous or equally spaced, nothing like that. And then we'll have the function values themselves. Let's have 4, 3, 31, and 84. And now what we can do is we can take each of these values and plug them into the actual function. Because essentially when we talk about x0, x1, x2, and so on, that's these values. So this is essentially x0, this is x1, this is x2, and this is x3. So how can we actually get the coefficients? Well, we take x0 and we start thinking about what will happen if we plug x0 into the Newton basis. So this term has x minus x0. So you plug x0 in here, you plug it literally in place of the x, and this term vanishes because it's x0 minus x0. And of course, it's also repeated here, so it vanishes from here, it vanishes from here, and any further terms, if we had any, would also vanish. So we know that a0 is actually equal to the function. So we may as well write it down. So essentially, in this particular case, we say that a0 is equal to 4 because that's what the function value is. So now what happens with x1? x1 is equal to 1. So we take x1 and we plug it into the whole polynomial. But you'll notice that here we have x minus x1 where x1 is being plugged in. So this term vanishes, this becomes 0, the whole thing becomes 0. This term also vanishes, we only have the first 2 terms. So we essentially have a0 plus a1 multiplied by x minus x0, and that's x1 minus x0. So that's multiplied by 1 minus x0, and that's equal to 3. So we can rewrite this, of course. We can say that in actual fact, let's wipe this out because it kind of simplifies, and we get simply a0 plus a1 being equal to 3. And from this result, we can immediately deduce that a1 is equal to minus 1. So the third calculation, once again plugging x2, I'm going to omit the workings here and just give you the final result. So we'll have a0 plus 3a1 plus 6a2 being equal to 31. And then the fourth calculation will be a0 plus 4a1 plus 12a2 is equal to 84. So this is easy to solve. You're not solving really a system of equations, because once you have this, you get this automatically, then you get this automatically, and so on and so forth. So it's very quick to solve. And once you actually get these values, what you get is a set of values for the a coefficient. So you get a0 equal to 4, a1 equal to minus 1, a2 being equal to 5, and a3 being equal to 2. And so you take these values and you plug them back into the Newton basis. So essentially you say that P3 of x is actually equal to 4 minus x plus 5x times x minus 1 plus 2x times x minus 1 times x minus 3. And this simplifies to 2x cubed minus 3x squared plus 4. And this example wouldn't be complete without a MATLAB illustration. So once again, I'm here exemplifying what we've just done essentially. So we have the interpolated function, and we also have a bunch of points. And if I run this, you can clearly see that the set of points we were looking for happen to coincide with the polynomial.